In the previous recording, I have discussed the applications of Biot-Savart to find the magnetic fields at the center of circular coil and at an axial point of circular coil. Now, the third application of Biot-Savart law is to find the magnetic field due to a long straight current carrying conductor. Consider a straight conductor XY carrying current I from end X to Y as shown in the figure alongside. Here the magnetic field is to be calculated at point P at perpendicular distance A from point O on the conductor. Since we are going to use Biot-Savart law, we need to suppose a current element at any point on the conductor. So we consider that elemental current or current element of length dl at point A, then join point A and point P. After joining, we have some geometrical values that we need to write. Let me share. Okay, that OP is a fixed distance of the field point from the conductor. R is the radius vector joining the source point and the field point. That is AP is equal to R and OA is equal to L. And angle YAP is equal to theta such that angle OAP is 180 minus theta. The magnetic field at point P, actually the elemental flux density at point P due to the current element of length dl at point A is given by Biot-Savart law as as you know, mu naught by 4 pi IDL sin theta upon R square. This is due to this small current element at point A. To find the total magnetic field at point P due to the whole wire, we need to integrate. But before integrating, remember that there are more than one variables. See, as the position of the source point or the elemental length changes, this angle changes, length L changes, and correspondingly R also changes. So there are three variables here. We need to reduce this expression in terms of single variable theta. We do this by considering the right angle triangle in this figure. Check the right angle triangle OAP. From there, remember that you are going to convert that dl and r in terms of theta and a constant. This A is constant because P point is fixed. P point is at a fixed distance from the conductor, so A is constant. So while converting, consider one variable and other constant as a trigonometric ratio. Now, L by A, if you want to convert L in terms of theta and a constant A, L by A is equal to cot, because this is B upon P, base upon perpendicular. So base upon perpendicular is cot theta. Here theta is 180 minus theta in this triangle. And you know, cot 180 minus theta is minus cot theta. So this implies L is equal to minus a cot theta. Now differentiating this equation, you get dl is equal to minus a. The derivative of cot theta is minus cosec square theta. So this gives dl is equal to a cosec square theta d theta. So dl is now converted in terms of constant a and theta variable, only single variable theta. Next, let us convert the variable r in terms of constant a and theta. Again, from the right angle triangle OAP, r upon a is h by p. That h by p is cosec theta. Here, in place of theta, the reference angle is 180 minus theta. So r by a is cosec 180 minus theta, and cosec 180 minus theta is equal to cosec theta. So this implies r is equal to a cosec theta. Again, r variable is also converted in terms of a constant and variable theta. Now, replacing those values in equation 1, we get here just in place. Check that. Mu naught I upon 4 pi. The same here. dl is converted to theta variable and a constant a cosec square theta d theta. Sin theta is same here, and r is converted to a cos theta. So now simplify this and get an expression with a single variable theta, such that you can integrate the equation to get the total magnetic field at point P due to the whole conducting wire xy. Okay. Now remember again that you will get total magnetic field at point P due to this whole wire by integrating equation 2 throughout the length of the wire in angular limits from theta 1 to theta 2. Okay. That means you are going to integrate that equation. Total magnetic field B is equal to theta 1 to theta 2 dV. Put the value of dV from equation 2 and integrate. The constants can be taken out of integration sign. So mu naught I by 4 pi a, all are constants. So they are taken out of integration sign and integrate with respect to theta. This implies B is equal to mu naught I by 4 pi a cos theta 1 minus cos theta 3. You remember that integration of sine, derivative of sine is positive cos, integration of sine theta is negative cos. So after using the limits, you get mu naught upon 4 pi a cos theta 1 minus cos theta 2. Now, as a special case, if the conductor is infinitely long, the angle theta 1 will tend to 0 and theta 2 will tend to 180 degree. Then equation 3 becomes mu naught by 4 pi a cos 0 minus cos 180. You know, value of cos 180 is minus 1. So V is equal to mu naught I by 2 pi A, 1 minus 1. That is, the result is V is equal to mu naught I by 2 pi A. This is for very long conductor, infinitely long conductor. That means if the conductor is infinitely long, and the field point is there, that angle will tend to increase and that angle will tend to decrease. So we use that limitation or limit. Now, if you consider a semi-infinite conductor, semi-infinite means we are going to find the magnetic field at one end of the conductor. That means origin lies at one end and field point is at perpendicular distance from that origin, and the conductor is infinitely long at one side only. This is called semi-infinite conductor. In this case, see, theta 1 is equal to 0, is equal to 90 degree, and as the length of the conductor increases, theta 2 will tend to 180 degree. So the case becomes like that, and if you substitute this value in equation 3, you get V is equal to mu naught I by 4 pi A cos 90 minus cos 180 and is equal to mu naught I by 4 pi A. Remember these results. Again, I want to say the numerical problems can be asked on the basis of general formula for finite length, or the cases expressed in boxed formula mu naught I by 2 pi A and mu naught I by 4 pi A as special cases.